share my screen. All right, so let's talk about the lab from Friday. Everybody can see my screen and hear me and everything?
Yep.
All right, so we want to go and we want to experiment with a couple of things. Before we can solve a problem, we have to understand the problem we're solving. We have to understand the individual tools that we have to solve this. So the goal of what I gave you last time was I gave you this link that takes you through kind of a series of examples of signals. And the two things that we're going to use here are our user-defined signals, signal user 1, signal user 2. All right, so the intention was for you to go through these examples first and build up that knowledge of how do these signals behave, and then start incorporating our knowledge of the fork system call and things like that in there. What we're going to do is we're going to experiment with these today. I did extend the lab to be due by the beginning of class next time. We might get a halfway start on it today to get you a stopping point, but let's see. But we want to go through, we want to understand each of these things and how the signals work. We saw last Wednesday that there was a difference. For example, I probably still have the page up here. Let me hide this. Was this the one? There was the difference between the sig kill and the sig t kill, I think it was, or sig interrupt and sig t interrupt. I think that's what it was. Terminal interrupt versus normal interrupt. And we saw one of them responded in the terminal, the other one responded from a user-defined process. But in this case, we're writing this all as user-defined processes in code, and we're going to use those built-in, well, not even built-in, but our user 1 and user 2, wherever it is in here. Well, we have up to those two that don't have predefined default responses from the operating system. All the other things have default responses from the actual operating system. All right, so let's go back into here. All right, and we've already kind of seen an example of this, but let's just walk through as they show the next level of things coming through here. All right, so basic, we have our signal handler, and we can have as many processes as we want decide to respond using the same signal handler. In this case, we're just having a single, we're not forking or anything. So we have this one thing, and this says we're inside the handler. All right, now this guy is going to say that whatever process this is, we're going to register ourselves to be interested in an interrupt signal. But instead of the default handling, which kills the process, if we run a process and then we hit Control-C from the command line, it kills it. Instead of the standard thing here, we're going to go ahead and associate the response with our signal handler. Okay, so we can think of our signal handlers at the operating system levels like a stack of signal handlers, and we pop until we hit the one that can handle the guy that we want. In this case, it's the most recent one that we've put onto the top of the stack. All right, so, and we'll see how that plays in here later on. So in any case, we say that we want to register ourselves to be interested in the signal. We're going to go through and we're going to do something an infinite number of times. It's kind of a stupid way of writing an infinite loop instead of just saying like while one or something. But we're going to go through and just keep looping, keep looping, keep looping. And we're going to just print out we're inside of main. We're going to sleep for a second, and then over and over and over and over again. Okay, so when we run this program, it's going to run. We say we're inside main. A second later, we're inside main, so on and so forth. Then we hit Control-C, so we send the interrupt signal externally. This guy catches it and handles it. It says inside handler function right here. Then we get a second later inside main, and then we can kind of force the thing to finally die out. This is like a control /quit thing, which has a default operating system response to it, which does something called a core dump, which is kind of like a log file or something. Unimportant for this. That was just the way they got out of their example. All right, so this is just a straightforward signal handler example, but all happening external to the program. This one's kind of unimportant to us in what we're doing here, but we'll look at it real quick. So we can choose to ignore a signal. So instead of associating, so like I said, by default, signal interrupt is handled by the operating system. Now we can write our own handler like we did up here to handle that particular signal, or we can say, you know what, I want to just bypass anything related to that signal and don't respond to it at all. So we can register an interrupt, effectively making our program uninterruptible by associating with this sig ignore, which is likely a handler that has nothing in it. My guess is it probably looks like this with nothing in there. Okay, and we see that this guy just keeps counting through, doesn't actually call any handler function, doesn't die off by the default thing, also doesn't get into any sort of example function. All right, so now re-registering signal handler. So we can go back to the default handler for a signal, kind of pass the buck, if you will. So in this case, we're going to go ahead and say for signal interrupt, we want to handle that through this function, signal handler function we're writing up here. This guy just prints out inside handler, but then he says, I want to re-register myself for the sig interrupt to be the sig default. Whatever the operating system is supposed to do under those conditions, I want to continue to do those things under those conditions. All right, so we go through, we have our infinite loop again, inside main, 3 seconds. We send our interrupt. It goes in here and says inside the handler. Then we update our signal handler to no longer have sigint be handled by our handler, but instead go back to the default. So then the next time we hit Control C, it exits out because that's what the operating system says to do under a signal interrupt. All right, so then we get into user-defined signals. So if we want to have, so all these examples up here were us doing things external to the program. All right, so doing our Control C to try to break out from the terminal. But now we want to have our processes themselves be able to raise individual signals. Okay, now a couple of things that we can do here. So we have a raise function. We also have a kill function. So raise used to send signals, a certain signal to the calling process itself. Return 0 if successful and a non-zero value if it fails. Kill function is used to send a signal, SIGDUM, to a process or process group specified by process ID. Okay, so understand the difference between if I raise a signal, I'm sending that information to myself, which if I have a handler, I will respond to that handler. So this is not doing a global notification. Raise is saying, I'm going to, let's call it indirectly, call one of my handlers if I have one of those. Or I could raise sig interrupt. I could raise sig interrupt, and sig interrupt would then respond using the default operating system response, which would kill the process, right? So this is just saying if I call raise inside of a process, what ultimately is happening is that process receives that signal just as if it had received it external to the running process. All right, and it's going to handle it however it would have handled it, like we talked above, whether it's handled by the default from the operating system or you have a specific handler. But the important part of raise is that it sends a message to itself, as opposed to using the kill function, which allows us to target a process ID. So this is one way we can use signals to communicate between individual processes. All right, so we can send a specific signal to a process ID through the kill command. So the kill function is used to send a signal to a process or process group. And we'll see examples here in a little bit. All right. So in this example here, we have our signal handler inside of handler function, and we go ahead and we register our user defined signal. So this is something that isn't all, this wouldn't be handled generically by the operating system. So we're saying for signal user one, which is just a free user signal, call this signal handler. So we'll say inside main, we'll raise the function, inside main again. And we see that this guy will have the inside. So we'll say inside main, that's this one. Then we raised it inside handler, and this was a local call to this guy by way of raising. So instead of calling him, we could have called sig handler directly here instead of saying raise in terms of the behavior we ultimately got. But instead, what we said is, look, we're going to raise a signal, and this particular process is going to handle that signal in whatever way it's supposed to handle that signal. All right, which in this case, since it was a sig user one, and we already had registered sig user one to call sig handler, it then calls sig handler. So there's our inside of handler, and then we keep going with our program, and we return here. Whereas if we had raised sig interrupt, in fact, I want to do that here. Might even be in the next example, but let's so we'll just put this inside of our one shot for right now. All right, so there's the output we just saw. All right, so inside main, inside handler, inside main. When did that happen? It's when we raised sig user one. Now, even though I've told this guy he should be interested in sig user one, if I instead say I want to raise sig interrupt. So I've said I'm interested in somebody raising the signal sig user one, and I'm going to handle it through this handler. But then I'm going to go ahead and just raise a completely different signal inside sig interrupt. And we see that we got inside main, then it raised sig interrupt, and the guy died because that was the default behavior of the operating system. Okay, so that's what raise does. Raise sends an individual, well, sends a signal to this process. All right, so here's one with a kill example. So we have our handler, we're getting our process ID. So we'll go ahead and say we're interested in calling our handler based on sig user one, just like we had before. We print out we're inside main. We go ahead and get our own process ID. In this case, we're not calling fork or anything. So we get our own process ID, and then we call sig user one using that process ID. The difference is that this is targeted, whereas, let's see, they actually don't do arrays in here. This guy is targeted. So instead of it calling myself directly raising a signal, now it's going by way of operating system and saying, call the operating system's kill command to send this signal to this process ID, which just happens to be me in this case. Okay, but I am leaving home and sending this message to the operating system and then letting the operating system signal handler send a message back to a very specific process ID, okay, which happens to be me. All right. So again, we get to our inside main, inside handler, inside main, same output, but the means by which we got that output is a little bit different. We sent a very specific message to a very specific place. All right. So now we should start moving down that path of thinking about how can we use signals to send messages to very specific process IDs. All right. So now here's some parent-child communication with processes. This is using the fork system call now. All right. So we have two different handlers. One is for the parent and one is for the child. The parent one just spits out, hey, I'm the parent, I received a signal. The other one says, hey, I'm the child, I received a signal. And then it goes to sleep for a second. And then very directed says, I'm going to tell my parent. This is get parent's process ID. That's what this function is. As opposed to up here, we got our own process ID. So this is how we get our own process ID. We call the function get PID. This is how we get our parent's process ID. We call the function get PID, get parent process ID. All right. So from the child handler, we're going to send a message through the operating system, through the inter-process communication portion of the operating system, to this dude. That's to our parent. And the message we're sending is sig user one. All right. So the parent's handler just spits something out. The child handler spits something out, sleeps for a second, then sends a message back to his parent through the operating system. All right. So now we go ahead and we call our fork system call. And what does fork do? So there's two sides to this lab. One side is understanding how fork works. We'll experiment with that a little bit here in a few minutes. And then understanding how signals work. And then how can we put these two things together to accomplish a task? Okay, so we have our fork system call. So this is our error checking for it. Don't worry about that. Then we ask the question, if the process ID that was returned was 0, if I'm the clone, if I'm the child, then I'll go ahead and register that I want this signal user one, to be handled by signal handler for child. Okay, that's what we do in that particular case. And then we just print out the child is waiting for the signal. All right, then we hit the pause function here. I want to go look at the pause function here in a second. So the pause function is inside of Unix standard, and it waits for a signal. So it effectively tells the current, I need to make this not full screen because it's doing that, not updating my screen for me when I try to type something. So the pause function just says, wait for some signal to occur. So it basically puts the the child on hold, but says, keep your eyes out for a signal. All right, we talked about signals kind of being like the observer design pattern last time, where maybe we would, we said that it's a good idea for the, oh, what did I do there? We said that it's a good idea for a object or a process to be productive while it waits for some something to occur, some event to happen, as opposed to sit there and just stare at it. In this case, the way we're using pause in our current example is we're just literally staring at the wall waiting for somebody to wake us up. All right, so we'll say that doesn't really follow the observer design pattern, but it shows us how the child or how pause ultimately works. All right, so if we spawn off a child, the child says, I'm interested in this signal. I want to call the child handler. I'll print out that I'm waiting, and then I'll call pause, which says, sit here and do nothing, waiting for a signal to occur. So that's what the child is doing. We've spawned off a single child, and we've said, wait. We need you to wait. All right, then we get to the parent process. Parent process says, so this is the else. If I wasn't the clone, I must be the original. If I'm the original, what do? I associate that signal with the parent. I'll go ahead and go to sleep for a second. Then I say I'm sending a signal to the child. So we go ahead and remember, if with the fork system call, fork returns either a 0 if you're the child, or the process ID of the child if you are the parent. Okay, so now the parent says, I'm going to send this signal directly to my child, or from a hint perspective for the project or for the lab, directly to one of my children. Process IDs or PID types, which I think we saw are just integers. So the parent could keep an array of all of its children. Every time it spawns off a child, it can keep that in an array so it can communicate with an entire collection of its children. And the thing mentioned process ID groups as well, but we can bypass process ID groups by just saying, hey, I have 11 children. I have an array of 11 integers. I can send a message to each of those 11 children by just calling the kill command 11 times with each unique process ID in there. Okay? That might take you down a interesting path related to the lab. All right, so the parent says, I'm interested in signal user 1, and I'll call the parent handler. I'll sleep for a second. I'll go ahead and say that I'm about to send a signal to the child. And then I'll use the kill command to make a phone call by way of operating system. Who am I calling? This dude. What am I sending them? This signal, which tells them to hit their handler for the, in this case, I'm sending it to the child, which should call the child handler. All right, so we run this guy. The child says, I'm waiting for some signal. So that's the child right here, waiting for a signal. Then he's just going to pause and sit there for a parent to raise that signal. The parent then says, I'm sending the signal to the child. Sending signal to the child. Then it uses the kill command to send this signal to this person. So parent sends the signal, and then they said, I'm waiting for the response. And now the parent waits for a signal to come back. The child, this guy now has released because the signal has arrived. It then calls the signal handler for the child, which says, I've received a signal from the parent. Child received a signal from the parent. Then it goes to sleep for 1 second. Then it sends a message back, sends this signal back to his parent, get PPID. His parent, which was on pause here, then unpauses, comes up to the parent handler and says, received a response signal from the child. Okay, so this is a full back and forth communication example between a parent and a child using the fork system called one time. So we've spawned off a single child process in this code example. So let's actually take this for a second. I'll paste this in here. Just see it run real quick. Make sure there's not any weird bugs. Child's waiting for the signal, parent sending the signal. Remember, we had the 1 second sleeps in there. Parent's waiting for the response. Child received a signal from the parent and then sends the message back to the parent. And now they've both terminated because they both paused and waited for the signal to come in. Then it terminated. Well, then they got the signal, they handled the signal, and then they moved on with life, which ultimately, when they moved on with life, what happened after the pause? So this guy blocked until a signal arrived. But after that signal arrived and it handled it, we hit this line right here, which is the end of this if else. This is not in a loop, so we just hit the end of the program and return 0. Same thing when we were the parent and we were holding on this pause. Once the parent releases, we'll also return 0. So we had 2 different processes that were alive here, and they both ended naturally after they both blocked waiting for some signal. The signal finally arrived. They handled that signal, depending on who they were, and then the program ended. Okay, so we know for the lab that we're going to be creating more than one child process. Okay, so we can go ahead and let's just take this one step further. And say, you know what? All this stuff right here, I want to do twice. Let's just say for int I is equal to 0, I is less than 2, I plus plus. So we're just hard coding in that we're going to have 2 children. I'm going to do all this stuff twice. That was weird. Oh, maybe it wasn't weird. Still seems weird. Must have just been spaced funny initially. All right, we'll call that okay. All right, so now we're going to do something twice. What are we going to do twice? Well, we're going to call the fork command 2 separate times. We'll make 1 pass. The first pass says, hey, if I was the child, I'm going to register myself. I'm going to wait for the signal. Then I'm going to actually wait for the signal. If I'm the parent, I'll go ahead and register myself for being interested in this call. I'll sleep for a second. I'll send a message to, this is one of my children for right now. We're going to create a collection of children in a minute as we just kind of move towards what you're going to need for the lab. We already know collections. We can create an array of integers, no problem. All right, so we're going to send a signal to the child. Which child? Well, the one we just recently created. That's the message we're going to send, because we're going to be looping through and we're going to be overwriting PID with our new child process ID. As of right now, we're not preserving the old one. All right, so we'll send a message to our most recent child. then we'll print out that we're waiting for a response. Most recent child gets their message. Well, the two are communicating now. The most recent child gets their message. When they send it back to the parent, what does the parent do? Well, first of all, this line right here in our parent, this guy blocks. So this guy says, we will not move on to the next child until the current child that we just spawned sends us our message. We are waiting for their signal. All right, so that signal finally comes in, the parent handles it, we move on, we hit this closing curly brace for our for loop, we spin up, we do the whole thing again, creating a new child who then wants to send a message to his parent, so on and so forth. So there's the first child waiting. There was the second child waiting. But now let's look through this. So we had our first child waiting for the signal. Parent sent the signal to the child. In fact, this might even be handy. Here, I want to just make a quick little change here. We'll see the parent sending the message to a very specific child. All right, so here's the parent sending a message to, this is their firstborn, let's say. Then parents waiting for the response. This is their pause command. Then the child receives it. The parent then receives the response signal from the child. This is then their handler. The child is waiting for a response. This is both children waiting for a response now. Let's see, let me go back to show you where that child waiting for signal thing is. That's in this guy right here. Child waiting for a response. So we had child waiting for signal right here. Then the parent sent a signal. Then we have parent waiting for signal. Then child received the signal. Scroll up to again. Child received the signal. Parents received the response, and we were done. All right. So there was the communication. Child is born and waits. Parent sends the signal. Parent then waits. Child receives the signal. Parent then receives the response from the child. But let's see what went down here. Our original child is spawned and is waiting for a signal. The parent sends a signal to this particular child, 264. Parent is waiting for a response. Actually, I'm doing 3 children here, not 2, right? Did I say less than 1 or less than 2? Less than 2. We're actually going to have 3 children at play here. That's okay. Still solves the problem. Okay, so here's our first child, 264. Parents wait. So the parent sends the child a response to them. Child received it. Parents then waiting for that response. Parent receives a response from that child. Okay. Then the parent spawns another child. So this loops back through. We call the fork system call again. So this blocked until the parent was able to handle it. We hit the end here. We spin back up. We hit fork again. If the process ID is 0, we re-register ourselves. And then we say we're waiting. Okay, so child waiting for a signal. Now, what I'm going to come back and ask here in a few minutes, you can think about it now if you want, but I want to finish doing this, is why are these two things right next to each other? Child waiting for signal, child waiting for signal. Parent sending signal, parent sending signal. These are two separate children, right? But we know that this child, well, presumably 647172, we know that this child was the third child, very likely by the number, the counting here, right? So this was child 1, 264, then 271, then 272. That seems like it probably makes some sense. All right. But we're seeing that after the first child, it seems like the next two children are both getting system time at the same time. Seemingly. We'll talk about why here in a minute. All right. So then the parent is waiting for a response from both of them. Child sends a response. Then we received a response signal from the child from both of them, and we end. So we see all the right things happening here. All three children were born. They sent a message to the parent. Parent sent a message back. Actually, other way around, right? Yeah, other way around. And then they all ended. Why do you think these things here are right next to each other?
Because they both have a process ID of 0, and they're probably stored in a stack. So the latter one was on top and got popped first.
Okay, what do you mean they both have a process ID of 0? You talking about this code here?
Yeah.
Well, this is just from the parent's perspective. The only reason the parent thinks that PID is equal to 0 is because that's what fork returns. So the fork system call here, it clones the current process. So step 1, that's what fork does. Clones the current process. And then because of that clone, we're going to have two versions of PID here. All right. So after this line right here, a new process has been created, but they are duplicates of each other. So the very next thing that happens, assuming we get past this if statement here, is we're sitting right here and we're going to ask a question. Who are we? Am I the child or am I the parent? It's not that the child's process ID is actually 0. It's that if PID, this local variable PID, if it equals 0, that means you were the clone, not the original.
Okay.
All right. As opposed to here in the else, when we sent a message to PID right here, this PID is a real value. I printed out PID in here, and I think so we'll see the numbers. This was the process ID of our first child, probably our second child, probably our third child, just numerically by these. I think this was the third one created. This was the second one created. All right. So the children don't actually have process IDs of 0. That's just from the parent's perspective that, well, actually that's from the child's perspective. If their process ID is 0, that means they're the copy.
Okay.
All right. So back to the question then. Why do you think these things are happening in this order? This is more of an operating systems type question.
Was my previous guess wrong with it being a stack?
Well, try to word it again. Stacks are probably related here, but you flagged your first response with they both have process IDs of 0.
Well, I'm guessing they're stored on a stack, because that's typically how systems work. So, and then the latter one would be on top, so it gets popped first, which is why we're seeing the latter one IO come out first.
Probably not. That's probably not what's going on.
Just the operating system somehow determining priority of which process runs first.
What is happening when we write this out to the screen? What is the operating system doing? It's doing input output stuff, right? And input output stuff to the screen is expensive. more importantly, for how operating systems work, when something is on the CPU and now it needs to do IO, which means now it needs to talk to the operating system and ask the operating system syswrite to ultimately write something out to the screen, which has its own set of rules or whatever associated with it, it's passing the buck. So in order to get from my program to this text being on the screen means that I actually got kicked off the CPU. So what we're actually seeing here is just the way that the operating system schedules these processes when they have to get back in line to get CPU time again, what we actually saw here. And this is where it's possible it's related to stacks, Noah, in that if the line to get back in is some kind of priority queue, which could be, it's called a heap, which could be implemented as a stack, or could do it as a linked list as well, I guess. It's possible that when they got back in line, they then got back onto the CPU in reverse order, depending on who was back in line. But I don't know that we can necessarily rely on that. Let's run it again and see if we happen to get the same backwards order again. Yeah, it looks like we did again. Let's just go one more try. Yeah, see, that one was in order. So there is no guarantee that they're scheduled that way. So what we're seeing here is when we print something out saying we're about to send a signal to the child, let's just go into the code here. This line to this line, the process, right when it issued the printf command here, got kicked off the CPU. And it did not get to issue this next command until it got CPU time again. So between claiming it was about to send a signal and actually sending that signal is an arbitrary amount of time. That is the amount of time it takes to display something to the screen, get back in line for the CPU, and then ultimately send the signal. Does that make sense? So we have a whole lot of leaving the CPU. Remind me, what's it called when we have to pack our bags and get off the CPU so something else can load onto the CPU? I think we brought this up a couple different times. What's the operating system term for a process leaving the CPU to get more CPU time later for whatever reason they left the CPU? You know, maybe they're naturally done with their allotted CPU time, or they got interrupted to do IO or something. What's it called when something gets booted off the CPU to have to go get back in line to get more CPU time later?
So when it gets blocked and then it goes back to the ready state?
It is, but so you just mentioned ready state. That ready state is part of the life cycle dealing with what's the phrase used. 2 words, CS, the letters for it. What's the phrase used for a process leaving the CPU to get back into eventually the ready state, like you said, when it would get back in the line?
Context switching.
Context switching. So context switching is what's actually occurring here. And the thing that's most important to us, not necessarily memorizing the phrase context switching, although you probably should know what that is that context switching is expensive. It uses a lot of system resources and has an arbitrary time associated with it. And we're recognizing that here. So whenever we're doing printf stuff, and the rationale for this is when you're testing your lab, you might get some behaviors that are like this, where things seemingly print out of order. And the reason for that is printf is not actually what's called fork safe. Because of the way printf actually functions, the way it actually makes the system call to the syswrite thing on the operating system. So you can't pay that much attention to the exact order that these things ultimately made it out to the terminal in. Okay, so at the end of the day here, when in looking at this example, everything that was supposed to happen seemed to happen. 3 different processes were born. The parent sent information to each process, yada, yada, yada. Okay. Go back in here. All right, good. So now we have some background into those things. Next thing I want to do a little bit just in our last few minutes is we want to experiment a little bit with how the fork system call works when we are doing some counting. So we want to see what happens with a global variable. Maybe we start this counter off at 0. We have this global variable. We have a counter that starts at 0. And what we're going to go ahead and say is the child is going to say counter plus here. And then we'll say child received a signal from the parent. We'll say %D here. And we'll go ahead and print out counter. All right. So in my current example, I have 3 children that are being created, right? And I'm telling each child to increment counter. Okay, each child's job is to increment counter. And we want to see what counter it prints out each time that one of those children receives a signal. Not paying attention to the order in which the next thing necessarily came out, because we just saw that that order can be a little random. Then we'll sleep for a second, and then we'll go ahead and let our parent know that we got their stupid message, whatever. Okay, so what we're exploring here is what happens when we have a global variable in our program. How is that global variable handled when we have a fork system call? Or in our case here, 3 fork system calls. So every single time the child handler gets called, we're going to increment the value of counter and see what that value is. What do you think it's going to be? Well, first of all, let me ask the question, what do we think the behavior of the fork system call is with regard to variables in the program? In this case, it's a global variable, but the answer is the same, even if it was a local variable in main. What happens when we call the fork system call? To the
reinitialize counter to 0 every time because this is like a global variable for this one program.
Okay. So with that in mind, what should the output be here? You're thinking it's going to be 1 a whole bunch of times?
Yeah.
Okay. I believe the answer is yes, but I'm not sure I'm convinced on the rationale. So this guy received a 1, then we got a 2, and we got a 1. Actually, that's pretty interesting. Why did it go to a 2? I'm thinking, was that a race condition? Called fork once. We said if we're the parent. There, I just want to run it one more time. Just want to see if I get that same behavior. I did get the same behavior twice. So I think we're running into the scheduling of how this child 1 got called. I think in this 1 second sleep here, the local variable inside the child handler was still the same. And that's why it incremented twice. But by the time we got to the 3rd one, it had reset back to, as you kind of pointed out, 0. All right. But in any case, if we're looking for, just since we're out of time here, just to kind of throw out the example here, when we call the fork system call, what happens? All the processes, the two process, the parent, well, we don't think about the parent. The parent already has it. The child gets a copy of all the memory that was being used for the parent process. What does that ultimately mean? It means that the parent or that the child effectively had all of the variables passed by value. All the variables were passed by value. All right. So let's stop here. What I'm actually going to do, because I want to finish going down this path, I'm actually going to, I changed the due date to the lab to be for next class, but I'm actually going to choose it to be due for Friday, because I want to come back next class and I want to keep going down this rabbit hole, because we want to explore how are these variables actually used? How are we going to have our children count up to see, do I have enough damage to kill mom? All right. So rather than having you work on it some more, I want to keep going down this example. All right. So we'll come back on Wednesday. We'll keep going through this example. We'll get a start for what you'll have for your lab. I'm not going to give you the whole thing, but hopefully this gets you pushing in the right direction. If you want to start thinking about it some more and start working on it, again, to experiment with it, this was the expectation that you went through and tried to understand how these tools actually work. All right, questions, comments, concerns, bribes. All right, I'll see everybody on Wednesday.